Okay, Rita, could you please introduce the session?
Okay, so welcome to the 14th LISA Symposium, and thank you for joining this parallel session 1 on LISA instrumentation. I'm Rita Dolesi of the University of Trento and INFN. And in this first part, before the break, our speakers will be Marie-Sophie Hartig, Sarah PACZKOWSKI, and Daniel Georg. So, and for the questions, please, questions may be submitted via the chat at any time. If you wish to ask a question verbally, please raise a hand or include a comment with your question on the chat. Questions from the live stream on YouTube are also welcomed. All questions will be answered at the end of the presentation. So we can, I believe we can start with Marie-Sophie Hartig of the Leibniz Universität, Hannover, Max Planck Institute for Gravitational Physics, speaking about tilt-to-length coupling in LISA Pathfinder, data analysis and lesson learned for LISA. Marie-Sophie.
Thank you. Thank you very much for the introduction. Let me quickly share my screen. Yes, I hope you now all see my screen. I'm happy to talk about tilt-to-length coupling today, which was a significant noise source in LISA Pathfinder and is expected to be a major noise source also in LISA. Therefore, I will present here our recent results of the analysis of the LISA Pathfinder data and what we learned from that in regard of LISA. Since my talk is the first tilt-to-length coupling talk, I'll start with a very brief introduction of this noise. So tilt-to-length coupling is the unwanted coupling of angular or lateral jitter of either the spacecraft or a task mass into the phase signal. And taking, for example, the example of the task mass jitter, this can look the following way. We have here a task mass which tilts, and therefore the beam path changes. Hence, also the phase signal would. Likewise, we refer to lateral jitter coupling as tilt-to-length coupling, since it only couples into the signal if the task mass in this case is a priori tilted. In terms of LISA Pathfinder, we wanted to measure the relative distance changes of the two task masses, which are the golden blocks here inside the electrode housing, or their relative acceleration. Therefore, there was an optical bench in between with all the optical setup. Tilt-to-length coupling, in case of LISA Pathfinder, was mostly the jitter of the spacecraft and hence the optical bench with respect to the task masses, which can also be interpreted as a jitter of the task masses with respect to the center of mass of the spacecraft. And it was the limiting, without suppression, the limiting noise source between 20 and 200 millihertz. If you want to know more about LISA Pathfinder, the higher frequency noise, I can recommend the pre-recorded talk by Leonard Visser. So in LISA Pathfinder, there had been mainly two subtraction strategies. First of all, the tilt-to-length coupling did depend on the alignment of the task masses. Therefore, at 3 times the submission, the task masses had been realigned for direct tilt-to-length coupling suppression. The first realignment took place after the engineering phase in March 2016, and it reduced, as shown here, the relative acceleration of the task masses from the red curve down to the green curve. So it reduced the coupling significantly, however, still significant noise remained. Therefore, there was a second strategy, a subtraction strategy. For that, the noise was fitted and the fit model was then subtracted from the measurement. This is shown as a plot at the right-hand side, where you can see again in red pre-engineering noise, and in yellow is the noise remaining after the subtraction. You find that you actually have higher noise at higher frequencies, since the noise from the fitting quantities was added due to the subtraction of the fit. So both models themselves are not sufficient. So what had been done during the mission was to combine the two of them. First of all, the task masses had been realigned for total length coupling reduction, yielding the green curve here, and then the subtraction method was applied to that residual noise, yielding finally the blue curve. So with that, total length coupling was nicely subtracted from the data during the mission. However, till the end of the mission, there was no real explanation of that coupling. So it wasn't understood why the realignment did not work as good as expected. And such an explanation would also be necessary to finally validate this suppression strategies which have been applied and which are also planned for LISA. And we don't really want to start LISA without having understood this noise. That's why we set up a new analytical model where all the coupling coefficients depend on the setup of LISA Pathfinder and also the alignment of the task masses. And in the following, I will compare that new model with the fit model, which has been used for the subtraction strategy. And apply that on the LISA Pathfinder data. Mind that in the fit model, we have 3 additional terms. There was also fitted how the displacement of the task masses induced a change of the measured delta G, and also how an acceleration of the spacecraft along the axis between the 2 task masses coupled into that signal. So these are not contained in the analytical model. The first series of data we investigated were that of the long crosstalk experiment, which took place in February 2017, and it was designed to test total length coupling. During that experiment, the task masses were brought to in total 12 set points, which means that they had been shifted and or realigned. And at this new position, a series of injections were applied. First of all, the spacecraft has been made jittering laterally, then angularly, and third, injections at different frequencies, a more complex jitter was induced. Depending on the set points, this injection has been applied in one plane and or the other one, and hence the data provide a very nice testbed for our models. So we first took the fit model and checked if it can also subtract these higher induced noises during the during that experiment. And this is shown at the figure at the left-hand side, where in red you can see the measurement, in yellow you can see what has been fitted. At the injection frequencies, which are 10, 12, and 17 millihertz, these nicely overlap, and hence in blue the residual is quite low. Also at higher frequencies, we see a nice reduction of the noise. The peaks you can still see here are at the multiples of the injection frequencies, and these are simply not covered by the linear fit model. We then did the same with the analytical model, which is shown here at the right-hand side. In red, you can see again the measurement, in yellow the analytical model, and since this did not contain the 3 additional terms, we fitted them additionally for a better comparison, and then subtracted both from the data, yielding the blue curve. You can also already see that the residual noise is a little higher. However, in all 12 experiments, we were able to reduce the total length noise at the injection and at higher frequencies significantly, telling us that the analytical model in principle works. So we went on comparing then the 4 coupling coefficients which were available in both models. And the comparison showed that in most cases they nicely overlap, which then also validates the fit model, telling that the coefficients somehow really rely on what has happened due to the realignments. Only in some cases for one coefficient we still find differences, and So the course of this is subject to an ongoing investigation. For time reasons, let me just say when we adapt the analytical model accordingly, or the general comparison accordingly, we find also coincidence in this case. So we have these two models coinciding and subtracting the injected noise, where the analytical model was very complex to evaluate, while the fit model does not yield any explanation about the dependency of the coupling on the test mass alignment. However, having the long crosstalk experiment, we can use the fitted coefficients to find a third model, which, like the analytical model, gives us coefficients and the dependency on the test mass alignment. This is because we had this 12 experiments, hence a set of 12 total length coupling coefficients fitted, which all dependent on the test mass set points. So these are 8 degrees of freedom plus an additional offset. So we can just have an overdetermined system of equation and can just run a minimizer to find that the dependency of this coupling coefficients on the test mass alignments. We did that, and for all the coefficients, the result of the minimizer nicely coincided with the fitted coefficients. So what we gained from the log crosstalk experiment was a verification of the total length suppression strategies in general, and we now know that also that we have finally an analytical model that can really explain the total length coupling in LISA Pathfinder. So we now take that and go on to other times of submission and also analyze that data. And first of all, there are of course the data of the engineering days, which I referred to before, where the task masses had been realigned for a total length suppression. And the realignments that had been applied are shown here in this table, and we can take these angles, insert them into our analytical model, subtract it from the pre-engineering noise, and what we find is the purple curve here, which nicely overlaps with the residual noise we had after the realignment of the task masses. So we can actually model that residual noise with our analytical model. We can also do it the other way around and take the model and find the coefficient, the angles for which the analytical model tells us that this realignment would have yielded a full suppression of the total length noise just by this realignment. And when we insert these into the model and subtract them, we again find in this purple curve, which overlaps with the result we got when subtracting the fit at this time of submission. However, the additional noise at higher frequencies wouldn't be present if you really perform the realignment, since it comes only from the subtraction. Okay, so with these angles, we would have said at this time of submission, we would have had a full suppression of the total length noise. I say at this time of submission because we still have to wonder if the total length coupling was stable throughout the full emission. And therefore, we investigated the stability of the total length coupling coefficients. And we actually found that they are changing. Mostly this coefficient, the CZ coefficient, did not only change for the task mass realignments, indicated here by the red lines, but also in between we see drifts, and particularly here at the beginning of the so-called cool down, where the temperature within the satellite was decreased, we find a jump of the coefficient. And of course, we wondered what could have caused these changes. Also, there was no task mass rotation applied. And from the analytical model, we must say that we can explain these changes really only by real task mass rotations. And particularly for this cool down, we would have needed a differential task mass rotation of 30 microradian. The task mass angles were controlled for most of the time, and also this time by the differential wavefront sensing angles, which did not change. So we assume that the beams must have been tilted for any other reason, such that this readout yielded a task mass rotation for correction. And so we wondered what could have caused a beam tilt. And there's one scenario that could actually explain it, and which has been investigated prior to launch. And this would be a bending of the optical bench due to the thermal stresses on the mounts. And then the beam would tilt, and this beam tilt would further increase due to further reflections. So the analytical tilt-to-length coupling model actually yields an additional measure for the stability of the optical setup. Okay, let me summarize what I just told you. We now know that tilt-to-length coupling laser pathfinder can be directly reduced by a dedicated task mass realignment, which is also necessary for a good tilt-to-length noise subtraction. We have for the first time an analytical tilt-to-length coupling model for laser pathfinder. We can find a comparable model having the data from a log crosstalk experiment using a minimizing routine. And furthermore, we know that the coefficients are not stable, but drift and jump due to temperature changes. And we know that we can use the analytical model, sorry, to examine the stability of the setup. And I promised you some lessons learned for LISA. And LISA is different in many ways. So there's no direct translation of the analytical model. However, we can also deduce some general takeaway messages. First of all, due to the, since we now have an analytical model, we have a validation of the suppression strategies, which are also planned for LISA. So we are now confident that it is possible to really suppress the tilt-to-length noise to a certain level. The suppression strategies are again a subtraction strategy, and Sarah will talk more about that in a subsequent talk. We know that the initial level of tilt-to-length noise can influence the quality of the result of that subtraction. We can know that the realignment can reduce tilt-to-length coupling directly. This is planned in LISA prior to launch. And given that still the tilt-to-length noise is a little higher than expected and we face any problems, we have a backup option since we can apply a calibration scheme comparable to the log crosstalk experiment, where we wouldn't even need the injections and can find the dependency of this coupling on some realignment parameters. And we know that the tilt-to-length coupling coefficients are not stable but drift, so they have to be recomputed regularly, and temperature stability would be nice. Thank you.
Thank you, Marie-Sophie, very much. So the talk was very interesting, very clear. So thank you. I don't see for the time being any questions. And there is one of David Robertson. Maybe if you have a quick answer, I don't know if it can be a quick answer. So, but he is asking for comment more on increase in noise at high frequency.
The increasing noise at higher frequencies.
Or maybe you
can you add a few more details to that question, please?
That's a short answer. So given that we are already a bit late, maybe you can take it offline, or you have 1 minute to answer.
Can you maybe?
Can I just ask the question a little more clearly, perhaps?
Yeah.
When you did your fitting, you increased at the very highest frequencies. The noise level went up a little bit. I just wonder if you wanted to comment a little bit more on that. That your fitting suppressed the noise in the range you're trying to do it very well. But at the very highest frequencies, the noise got a little bit worse. I was just looking for a comment on that.
when I showed the result of the long crosstalk experiment, I can quickly go back. Then we didn't only had the noise at the injection frequencies, but we had also the decrease at high frequencies. And this is the region where we originally had the bump. So you find here the 20 millihertz, and the total length coupling bump was going up till 200 millihertz. So by the subtraction of that model, we always decreased the noise at this bump, which of course also did depend on the test mass alignments.
Okay. Thank you very much, Marie-Sophie. Maybe you can add some more details offline, and we go quickly to Sarah PACZKOWSKI, that we talk about post-processing subtraction of tilt-to-length noise in LISA. Sarah, you can share your screen.
Hello. Thank you very much for the introduction. I hope you will soon be able to see my starting slide also. This talk is about how we can subtract the tilt-to-length noise in LISA in the data processing. And today I have the opportunity to explain this to you on behalf of our little team, which is listed here and which consists of Roberta Giusteri, Martin Hjortsen, Nikos Karnesis, Jörn Fitzsimmons, Gudrun Runner, and Gerhard Heinzel. So this little talk is structured as follows. In the last talk, you have already learned what tilt-to-length noise is and what we saw about in LISA Pathfinder. So I will just briefly highlight the aspects which are different in LISA. We have developed a procedure of how to subtract tilt-to-length noise in the post-processing, and I'll try to walk you through it with a little sketch. Then I will show you the results which we obtained with this procedure in our nominal configuration. And then at the end of the talk, I'll summarize the results and the steps. So let me continue with 2 facts about LISA, which are very important for this talk. So first, let me remind you that each of the 3 LISA spacecrafts hosts 2 moving optical sub-assemblies, or in short, MOSA. So they contain the telescope, the optical bench, and the gravity reference sensor with the test mass. And you can see them here as the golden cubes, these black squares, and we marked the telescope in orange. And the second important thing to know for this talk is that the measurement of the changes in proper distance in between the 2 test masses along one arm is actually split into 3 interferometer measurements, as also shown here on the right. So the first is the test mass to optical bench measurement in a local spacecraft we call Spacecraft 1 here. And then we have the measurement of the changes in relative distance in between the 2 optical benches on the distant satellites. And it is followed by the measurement of the test mass to displacement with respect to the optical bench on the far satellite in Spacecraft 2. And now this talk focuses on the intersatellite interferometer measurement, or in short, ISI, which is in between the 2 spacecrafts. Then in the last talk, you already learned that tilt-to-length noise means that an angular jitter or tilt couples into the longitudinal phase readout, which is used for a length measurement. And on the right here, you find an example for this geometric tilt-to-length coupling of a single MOSA. So in this case, and for small angles, the tilt-to-length noise, delta P, is proportional to the misalignment between the beam and the center of the rotation. This is denoted as Y here, and the jitter, eta. And this results from misalignments in the optical system. So in general, tilt-to-length noise is the combination of geometric and non-geometric effects, such as wavefront errors. So in this talk, we will focus on LISA in the intersatellite interferometer, which is mainly driven by the Moser angular jitter with respect to the incoming beam. And if you would like to know more about tilt-to-length noise in LISA in general, I would recommend the talk by my colleagues Dervé and Alvarez on EFOCAT simulations for tilt-to-length noise analysis in LISA, which is one of the pre-recorded talks here. So the tilt-to-length noise mitigation in LISA is planned to be done in several steps. So here on the right, you see the estimated level of the noise in TDIX after each of these steps. So after careful integration, tilt-to-length noise is estimated to lead to the TDIX output, which is shown here in pink. And after the application of the dedicated beam alignment mechanism, we expect to be able to reduce the noise such that we reach the green curve here. So this is unfortunately still above the requirement for the instrument noise, and it corresponds to a predicted in-flight tilt-length coupling values of 2.3 millimeter per radian. So this last step here, from green to black, is what this talk is about. So in this black trace, the remaining tilt-to-length noise is no longer limiting, and we are below the required noise level. And so this assumes that the TTL coefficients of around 2.3 millimeter per radian have been estimated to within an accuracy of 0.1 millimeter per radian. And so what you can clearly see here is that unless mitigated, tilt-to-length is a major noise source in the TDI output data. And in this talk, I want to show you that we can indeed estimate the TTL coefficients to the required accuracy and subtract tilt-to-length noise coupling. And this subtraction is planned to be part of the initial noise reduction pipeline, or short INREP, which brings L0 to L1 data. And if you want to know more about this pipeline, please have a look at the talk by Shweta Shah in the instrumentation parallel session tomorrow. So all that said, let me try to explain you the procedure with one example. So assume that in reality, or as we also like to say in Mother Nature, we only have the jitter of Moser 3.1 along phi at a given time, t0, and we have the sine wave shape. And we assume that all other Mosers and spacecrafts are perfectly quiet. In this example, we furthermore ignore that we have laser frequency noise and assume also different tilt-to-length coupling coefficients concerning received or short RX and transmitted beams, TX, alongside a few other assumptions that I won't go into detail here. So if we have that, then the impact of tilt-to-length coupling onto the measurements can be modeled by a linear model in 2 degrees of freedom. Always it's a coupling coefficient times a true Moser jitter. We can then split up these contributions into the RX and TX path. And in this example, this expression becomes more simple because we just consider a phi rotation. So we just have to cope with this bit. And then nominally, so outside from the simplified example, we would have 4 coefficients per Moser. And so we have 6 Moser, and therefore in total 24 coefficients. So for the interferometric measurement of this example jitter, also the phase locking is relevant. Indeed, this method is used for frequency stabilization to one primary laser. And in this example that we are going through now, we chose the locking scheme A, which is shown here on the right. Okay, now let us consider the interferometric measurements that we are dealing with. So one is the so-called differential wavefront sensing, or short DWS measurement, which is a measurement of the rotation that we experienced. But then we also have the two direct tilt-to-length coupling effects in the longitudinal measurements in the intersatellite interferometer 3.1 and 1.3. So the RX effect is in the local spacecraft and the TX effect in the remote spacecraft. And with that, we already have the sine wave jitter at the original time and delayed by 1 time the light travel time along the arm. Then, considering the phase locking configuration A, we obtain so-called echoes of these pulses also in the intersatellite interferometers 2.1, 1.2, and 3.1 with the corresponding delays. So we call this echo type 1, and they are due to the phase locking. So when we look at what we can see from this, then later from LISA down to Earth, then only the DWS measurement of the rotation and the interferometer measurements will be available via telemetry. So the true jitters will not be known. And we then apply 2 parts of data processing to this. So part 1 is shown on this slide. And here in the right-hand side of the diagram, we start with the fact that we have a measure of the jitters via the DWS. That means they are the true jitter plus some sensing noise. Then we apply our TTL model to these measurements to obtain an estimate of the respective TTL coefficient. And or in better words, of the contribution corresponding to this respective coefficient. And since the true values are not known here, we put a scale factor instead. And so like this, we have an estimate of the tilt to length impact in the longitudinal measurement. And then in the second step of the data processing, we apply time delay interferometry to both the original longitudinal measurements as shown here on the left. And that's like what is always happening. And we also do this for each of the estimated tilt to length contributions. And then TDI undoes these echoes type 1 from phase locking, and it adds the same echoes to all data streams, since the exact same delays are applied as are illustrated here in this TDIX picture on the left. So in the next step, we estimate the coefficients via noise minimization between the sum of all these TTL and TDIX contributions and the longitudinal TDIX measurement. And then if we get them, and in reality, it's also more complicated than just looking at TDIX. However, for this example, this shall be enough. And well, then these are used to multiply the pre-computed terms, and they are all summed up. And if you do that right, you get the same amplitude as you have in the original longitudinal TDIX measurement, and then you can subtract and get rid of that. So let me proceed with a few more details on the TDL coefficient estimation, also beyond the simple example. So this is possible only after TDI because you have to get rid of the laser frequency noise. However, the tilt to length noise is then mixed in TDI from the different MOSAs. And let's have a look at TDIX for one example. For example, ITER in here. So you can see that already we have 8 coefficients just along ITER and just in TDIX, and they get all mixed together. And in total, you have 16 coefficients in TDIX. And to estimate the total 24 coefficients, we make use of TDIX, Y, and Z. And we estimate them on a 24 hours time scale, where the changes in spacecraft separation are negligible, which means that we can have this linear TTL model after TDI. And in fact, we don't use X, Y, and Z to estimate the coefficients, but we transferred them to A, E, and T as given here. and then estimate the coefficients via noise minimization in frequency domain as described here. And we use A, E, and D together at the same time. So with this, I would like to come to the results of our nominal with our nominal simulation setup. And I'm sorry, I'm aware that I'm running out of time. So we use an open loop simulator with all coefficients set to the nominal value of 2.3 millimeter per radian. And so we don't also consider tilt to length noise in the test mass interferometer. We have a number of essential noise sources included, which are given here with their respective values at 0.01 hertz as estimated from current LISA noise budget. Okay, so I have to speed up a bit. Then in our nominal configuration, here is a plot for the TDIX output and the estimated tilt to length contribution in red and compared to this requirement. And if we start to subtract in the time domain using the true simulated values, we obtain this Sine curve. And if we use the values which we estimated via noise minimization, you get the blue crosses here, and the difference is pretty small, as indicated here in green. And yes, so we fulfill the requirement of 0.1 millimeter per radian. And what else? Yes, you can find more details in our paper quite soon. And with that, I would like to already conclude and say that the remaining tilt length noise has to be subtracted in post-processing. We have to use the WS measurements to estimate the tilt length contribution. And this method that we presented relies on noise minimization. Yes, and with our simulation based on the current knowledge, that worked. And we have also validated the methods for different noise scenarios. And in the future, we will test the procedure for more realistic scenarios, such as gaps, glitches, and gravitational wave signals, to show that we still fulfill this. And we will also continue testing with other and more realistic simulators. And with that, I would like to thank you and apologize for the delay.
Oh, you are just 2 minutes late, so we have still 3 minutes for questions. Thank you very much, Sarah. Your talk was very clear and interesting. Is there any question for Sarah? Otherwise, I have one. You mentioned in the last slides the fact that you will repeat your analysis, or considering the presence maybe of glitches, other source of noise. So what do you expect will be the impact of those features in these procedures?
So I think the impact can, of course, depend very much on the number of the glitches which we have, and then their amplitude, and then also the frequency range, because now we fit between 1 millihertz and 0.1 hertz. So it depends on where which frequency range of the spectrum they affect and how broad they are. Yeah, I think those are a few of the criteria. And yeah, I think also it will depend on maybe if they occur in different interferometers at the same time or not. So that's what I see now, but we hope to have, good results.
Something that you have to study and to investigate further.
Yeah.
Okay. Thank you. Any other question for Sarah? I don't see any questions in the chat. Maybe the people need some time to think about what you discussed. Maybe they will send or questions later. Thank you again, Sarah. And so we go ahead with the last talk of this first part before the break that will be given by Dan George. And the title is Using Fisher Matrices to Constrain Tilt-to-Length Coefficient within TDI.
Hi, thank you. Hi, I'm Don George, a graduate student at the University of Florida. And today I wish to talk about some of the work that we were doing to constrain tilt-to-length noise using fish information. This work was supervised by PEP, and also in conjunction with Paul Fulda and Guido. I also wish to thank Sarah and Marie for providing some context on this problem. But I also apologize for any possible confusion because we use slightly different nomenclature. So let's start with the motivation. A MOSA, if it jitters, can introduce up to 50 picometers per root hertz length noise, as you can see here. And so we wish to subtract it, and the question we wish to answer is how well we can remove tilt-to-length noise in the context of time delay interferometry. So to correct TTL, as Sarah mentioned, we need the DWS witness channels to measure and keep track of how the angles change for all the different degrees of freedom. And using these witness channels, we can calibrate TTL and remove it in post-processing. And so we answer this question quantitatively using the fish information, which lets us to calculate the lower error bound on each tilt-to-length term, and furthermore quantify the residual after subtraction. And also it helps us to check how it depends on the residual spacecraft jitter model that you consider. So some assumptions that we make is that, so we start with TDI 2.0. We're using the simple Michelson interferometers X, Y, and Z for in-plane and out-of-plane and roll degrees of freedom for the spacecraft and MOSA jitter. And because of the magnification in the science interferometer, we're mainly only concerned with the science interferometer tilt-to-length coefficients. And for simplicity, although these tilt-to-length coefficients can change over a wide period of time, for the time periods that we're interested in, we're going to assume that these coefficients are static. We assume that we have some noise floor along with the tilt-to-length, and we assume that this is not contaminated by laser frequency noise because we assume that we know the delays along the arms perfectly well. For a more realistic case, we assume that we have a frequency plan. And in our case, we assume a PLL scheme with the primary laser being on MOSA 1. And I will eventually present some results that show how tilt-to-length differs for different cases. So case A being the LISA requirement jitter, and case B being one of the models that's being used in LISA Sim and its noise profiles. So this is the model that we consider. So if we just look at the science interferometer signals, and we're just looking at the tilt-to-length, if spacecraft 1 jitters, it obtains these tilt-to-length noise terms. And this is denoted by K1RX, which is the tilt-to-length associated with MOSA 1, and it's due to local jitter on MOSA 1. And Psi1 is our DWS signal that measures the change in angle. And similarly for MOSA 1 prime. Of course, the other spacecrafts can also jitter, and this is what we see. If spacecraft 2 and 3 also jitter, we get these additional terms being measured on spacecraft 1. And so K2 prime TX and K3 TX, sorry, this should say TX, is telling you that this coefficient is due to jitter from a far spacecraft. Of course, these are not the only terms in the interferometer. Obviously, we want gravitational waves, but if we have other noise terms such as laser phase noise and test mass acceleration noise, we wish to characterize these and get rid of laser phase noise. And so we can't apply the Fisher matrix formalism on the science interferometer signals, and that's why we need to move to TDI 2.0. So TDI 2.0 accounts for flexing arms while still removing laser phase noise. So this TDI combination is some algebraic quantity which is appropriately time shifted versions of the interferometer signals. And what we're mainly interested in is the TTL terms. So if you look at the time domain part of TTL and take the Fourier domain, the Fourier transform, this is what we see. So again, we have the K1 Rx times psi1, except now this is the Fourier transform. We see the K1 Tx with some phase, and this phase comes entirely because of the time delay that's introduced in TDI or the physical delay that it experiences. And so because of this delay, we can find these coefficients independently, which we'll see. One may notice that some of the coefficients are clumped together, which means that we can't disentangle it if we just use TDIX. And this is H is the transfer function that we have for TDI 2.0. And for this slide, we just assume that the delays are equal, just to make the equations a bit more compact. Okay, so we saw what the TTL form looks like, and now we have to look at the noise floor associated that we consider. So in case A, we have the solid black curve that's dominated in the low frequency regime by test mass acceleration noise, and in the high frequency regime by shot noise. Case B is this dashed dot curve, and you can see the main difference between these two curves, the Lisa sim and the requirement, is that we also consider some gravitational wave background. So you can see that these noise curves are very similar. So let's move on to the DWS signals themselves, which is one of the most important parts of the results. So if we, or impacts results the most. So if we have, if you consider case A, which is this blue curve, Lisa requirement, it's similar for both the spacecraft and the MOSA. This orange curve is Lisa sim, and it has some fall off in the high frequency regime because we expect some fall off due to the natural jitter, the natural inertia of the spacecraft. And this will play a big role in our results, as we will see. We have something similar for pitch as well, or out of plane jitter. And here I've just shown you how the spacecraft and MOSA jitters are combined. You can see there's some symmetry in yaw, but not in pitch because of the roll aspect of the spacecraft. So how can we use fish information to predict the errors? So what you get from the fish information is the covariance matrix, which is just the inverse of the fish matrix. And this covariance matrix is just the error covariance matrix, and you can find your residuals from this matrix. Now, if you're interested in individual components, you can use what's called the Cramer-Rao bound, which tells us that the lower bound error on our coefficients is limited by the covariance matrix itself. And here we have the integral form of the fish information. So we're just integrating over Fourier frequencies and considering the slopes of the TDI combinations, TTL terms, with respect to a particular coefficient. And so, as you might guess, since we're dealing with the Fourier domain, we avoid lengthy time domain simulations. These calculations are very quick and easy to modify the signals and the noise, and it kind of helps in understanding things a bit better. But these fish information simulations have to be cross-checked. And we do this with time domain simulations for both cases. And how we do this is that we have some Monte Carlo simulation with 5,000 realizations of the noise. We inject some coefficients and create this artificial data from a uniform distribution. And then using the DWS witness channels, one can do a least squares fit to estimate these coefficients. And once we've done that, you can create a distribution for these parameters, for these coefficients, and just read off what the standard deviation is for a particular coefficient. These can then be compared with what we get with the fish information. Case B has a lower number of simulations just because Lisa sim, is a much more computationally expensive software. So here are our results on the uncertainties for individual coefficients. And here we just show TDIX. So the C and D terms are our coefficients in yaw and in pitch. And in these two columns, we have the values from the uncertainties that the fish information matrix gives us. And in parentheses, we have the values cross-checked from the least square solution. And so you can see that the fish information predicts only the uncertainty, not the values themselves. And you might notice that some of these coefficients are coupled together. You might think that you can't disentangle it, but if it turns out that if you use TDI X, Y, and Z, that you can find each coefficient independently. And this is useful if one finds some problem on a particular MOSA. You can work backwards and see which MOSA might be problematic depending on the coefficient that you get. And so this will help with future alignment problems. One major difference between these cases that you can see is that in case A, we have about 5 micrometers per radian uncertainty, but in case B, we have about 200. And remember how I said that the noise profiles are very similar? This means that this difference has to be purely from angular jitter. So again, these are the DWS curves for yaw. For case A, which is this blue curve, and case B, which is this orange curve. And because of the very low power that we have in case B, which we expect from the natural inertia of the spacecraft, this leads to lower calibration accuracy. And this is not to say that the LISA requirement values are much better, but one has to be careful because the LISA requirement jitter is not realistic. And the accuracy that you would get if you were to use a LISA requirement jitter is misleading because of this large difference in power. But all is not lost. Even though the individual values for the coefficients may be a bit high in case B, what really matters is the overall subtraction or the residual that you would get after 5 minutes. Okay, sorry. So we want the residual to be below the noise floor. And if we have some noise floor that we get from the previous plot, one can see how the residual of both cases look like. So you can see that the residual predicted by the fish information matrix in case A is below 1 picometer per root hertz for all the frequency bands. And this is about 1,000 level suppression if you assume that all the coefficients are, let's say, 5 millimeters per radian. But however, this is again not a very realistic jitter profile. Case B is still below the noise profile, except it's a bit worse than the case A, again, because you have a more realistic jitter. But we are still below the noise floor, which is good news. And it's below about 10 picometers per root hertz for all the frequency bands. So this is the plot with all the curves in case anyone was interested to compare them with each other. But yes, for future work, we hope to consider more mature jitter models. And in the event that these more mature jitter models produce residuals that are above the noise floor, one can investigate what happens if you inject jitter at high frequencies. And because of the framework that we have, this is easy to do because we have the model to put in any kind of jitter for the spacecraft or MOSAs. And because this is a space mission, we don't know what kind of noise profile that we expect. And so we want to consider what happens if you have some unknown noise profile, if we can predict this, and also if we can handle any glitches that are given to us. But thank you for listening. Any questions?
Thank you very much, Don. We see if we have some questions. So David, Do you have to worry about mosa-to-mosa jitter on one spacecraft, or is that small enough to be neglected?
That is one thing that we haven't considered. So the jitter that is common in both MOSAs is the spacecraft jitter. But you can construct a model where the spacecraft is silent and you just have all the noise in the MOSAs. At that point, they would be correlated, and I think the results would not change much.
Okay, David, it's okay. Maybe I have a question. You also are mentioning the possible impact of unknown noise sources on your analysis. Which is the worst kind of noise that would make your analysis much more complicated or difficult? Is there a specific kind of noise with some features in this spectrum that would make everything much more complicated?
So because we have, because the higher frequency jitter helps us, any additional glitches that would show up here would hurt us if we don't have commensurately larger spacecraft jitter. So that would hurt us here.
Okay. Okay. Any further question for Don? So maybe people will think during the break about further questions. So we thank Don again for his beautiful talk, and I think we can have the break, and we can reconvene in 15 minutes, or better at 21:15, so 9:15. Okay. Andrew, are you there? This is really tough. Harry, is Andrew there? Is not present at the moment.
No, I'm here.
Harry, no, I just I noticed that the next part of the session, the duration is from 9:15 to 35 minutes past the 10. That means 1 hour and a half.
Yeah.
Is that wrong or?
No, why would you think it was?
Because it's three talks of 20 minutes, Aaron.
Oh, yeah.
So that's why I was confused.
Yes, hang on.
Is there a talk that it's longer, or it's just a mistake in the schedule?
So it finishes at 22:15.
Yep.
It's finished at 22:15, correct? It's not 22:35.
No, the final box is actually blank. There's nothing in that that box.
Okay. So it's they are all 20 minutes talk.
Yeah.
Okay. Great.
We didn't use the final box.
Okay.
Andrew's clearly pushing the coffee break right to the limits.
Will we start or?
Yes, we can start with it.
I go. Okay. Welcome back again to this parallel session 1 on LISA instrumentation. I'm Rita Dolesi, and in this second part, we will listen to the talks of David Robertson, Henri INCHAUSPE, and Nils Frederik HASSELMANN. The questions will be answered at the end of the presentation. You could write them in the chat, or you can ask the question verbally, just raising your hand, and also questions from the live stream on YouTube are welcome. So I think we can start with David Robertson, University of Glasgow, speaking about optical couplers for LISA.
Thank you, Rita. Let me just find my pointer there. So, as Rita says, what I'm going to talk about here is optical couplers for LISA. This clearly is the work of more than just myself. It's really for the UK OB LISA team. And in particular, I'll point you at Bill Brzezowski, who's done a lot of the modeling work here. So to start us off, the question is, what do I mean by optical couplers? Whereabouts in the whole LISA optical system do they sit? So if you go for this cartoon LISA optical system that I have in the top right-hand corner, you can see there's the laser, the amplifier, the modulation system, whole complicated array of optics there, which I'm just putting into a black box. And they produce about 2.5 watts of light that comes out through a single mode optical fiber, this Newfern 1060L fiber, and the beam inside that diameter is constrained in a core of about 8 microns diameter. And that brings the light down onto the optical bench. And on the optical bench, what happens is you have to take this light from the optical fiber and produce a free space beam that is a diameter of about 2 millimeters. So you have to expand the beam up a factor of about 250, and you have to collimate it extremely well. And that beam largely then goes on, it does various other things in the optical bench, which we will ignore entirely. And the main power actually goes straight to the telescope, where again the beam is expanded up and transmitted to the far spacecraft. Now, as we've seen from Jeff's talk earlier, the constraints on the beam that's transmitted to the far spacecraft are extremely tight in terms of wavefront quality and so on. And that in turn means that there are tight constraints both on the telescope and on the beam on the optical bench and how well it matches to the telescope. And that's largely what I'll be talking about here. And just as a reminder from Ewan's talk earlier, the optical bench is a little more complicated than I've described it. The other important thing for the optical couplers is that a little bit of the beam on the main optical bench goes to a second optical coupler that transmits light through a fiber to the adjacent optical bench on the same spacecraft. And this allows us to do the phase comparison essentially between the two lasers on the two different optical benches. So that gives you a rough idea. In practice, what's an optical coupler look like? Well, again, there's this very simple sketch diagram here in the top right-hand corner. Essentially, all that you need is an optical fiber with a very nice end on it and the appropriate lens at the appropriate distance from the fiber with the appropriate orientations. And that will produce a beam that has the right physical properties. And here, particularly, we're thinking about the waist position of the beam that comes out of this assembly and the size of that beam waist. And I've listed in the left here some of the requirements that there are on the resulting beam. And in particular, for matching to the telescope, we need to know where the location and the size of this beam is with, well, it doesn't look like huge accuracy in terms of we want to be able to place the waist position within about 0.3 of a meter. But it turns out for a beam that's the size that we're dealing with, about 2 millimeters diameter, that's actually an extremely tight requirement. It requires that the fiber to lens spacing is constrained to within less than 10 microns typically. And there's a whole pile of other constraints that also come along with it in terms of the beam quality, this wavefront flatness, the beam pointing stability. Obviously, it has to be able to handle this 2.5 watts of optical power. We want to minimize the number of surfaces in the optical path in total. Every time you have an optical surface, you have the chance for scattering, you have the chance for a little bit of loss or whatever. So we want to minimize the number of optical surfaces that the beam goes through. And we also want to, as far as possible, minimize the power density on those surfaces as well. You're much more likely to have laser-induced power damage if you have very high light intensities on particular surfaces. And another thing we want is to have extremely low scatter and backscatter from it. That's another important constraint. So, as you'll see in a couple of the slides already, the system we've gone for is, as you can see in the picture here, essentially almost as a bonded together. It's using hydroxy bonding to bond together a block in which the fiber is mounted, some few silica, essentially lumps, very carefully known lumps that produce, essentially control the optical path and the lens on the end of it. And the reasons we've gone for this particular sort of construction, there's a number of different reasons that are driving it. As I said before, we need to control the spacing essentially between the end of the fiber at this interface here and the front face of the lens. We want to control that to of order 10 microns or so. We need to be able to adjust that. In the end, we will need a custom lens. At the moment, we're using off-the-shelf lenses, but for the particular requirements for laser, we'll actually need a custom lens, and I'll come back to that later. Pointing stability, again, I said was an issue. If the beam from the fiber coupler is changing in orientation, then obviously that changes the alignments later on down the optical bench, and that can lead to problems. So there's quite a tight requirement in that, and we meet that quite nicely. So for various reasons, we've gone for this sort of quasi-monolithic construction where we have hydroxycatalysis bonded the fiber, the spacer, and the lens all into one unit. And that has a number of advantages. It keeps the lens and the fiber end very tightly constrained relative to each other, so you don't really get any beam pointing changes with, for example, temperature changes. It minimizes essentially the interfaces we have between glass and air. Essentially the only interface you have in this is the final output of the lens. And it also means that the beam power density at that is very low. In LISA Pathfinder, for example, essentially we had a naked fiber end, a space, and then a lens. And there, the power density at the end of the fiber was about 300 times what we'll get even with the much higher laser power we're using in LISA. And also the backscatter from this assembly, and there are measurements which I'll point you to later, is extremely good. So to give you an idea of the build process, as I said before, we have the optical fiber, you can probably see here coming up, mounted in a fused silica block. And then once it's been mounted in there with very tight constraints, the front of the block is polished very, very flat, and we bond a cover slip onto it. And that means already that the fiber end is protected from damage or contamination or whatever. Then in order to control essentially the waste position, we need to control the spacing between the fiber end and the lens. And that's kind of what you're seeing in this picture in the second, in the top right-hand corner, where we have the fiber essentially beam expanding out of that, and we have the lens held in front of it. And there's kind of two things we're doing here. The lens is mounted in a hexapod, so we can control its orientation, its lateral position, its angular position and maneuver it around so that we end up with a beam out the front of it that's something close to what we want. It doesn't have to be exactly right, but something close. And when we have that, we do two things. We measure the separation between the lens and this fused silica block with some micron level precision. And we also characterize the beam out here. We take about 8 or 10 measurements at different distances along the beam. And we're doing this with specific pairs of lenses and sort of fiber assemblies here. We then take all this data and throw it at a model, which I'll come back to in a moment. And we use that to predict what length of spacer we actually want to get the required waist that we're looking for. So that's why, even though you're measuring putting this thing up, measuring the beam out here, it doesn't have to be exactly right. As long as your model can predict what you need to put in as the space from these measurements, then that's enough. So as I say, the next stage is to try and make sure that the optical path length in glass is exactly right at the few micron level. And we do that using this slightly wedge-shaped block here. So the wedge-shaped block is pretty much exactly the right length, but to do the final adjustments, we can either essentially slide it up or down the slope a bit, and that changes the optical path length through the block. And that's how we control to the precision we need at a couple of microns what the optical path length is in the glass. Then finally, we bond the lens onto the front of it. So a little bit about the modeling. I'll not do a huge amount about it, but there's been a lot of work gone into this to make sure that the model really reflects reality very well. So the modeling is done in Zemax using its physical optics propagation module. And it's actually an iterative process where there's a MATLAB wrapper around the whole thing that optimizes 6 parameters to optimize the fit. So we've got quite a complicated fitting process, and you can see some of the output from it here. Essentially on the top right-hand corner, it's the errors in the fitted parameters and how they're reducing in size as the number of iterations goes up to about 40 or so. The fundamental output from all of this is, does the model actually fit with what we're getting? So on the bottom right-hand corner here, you can see one of our very good results, in fact, where the blue line and the blue crosses are the actual achieved results for the beam profile, and the red ones are the target measurements for the same thing. So you can see it is actually an extremely good fit, and the waist position actually is, in this case, to within about 40 millimeters of what's required, which is well within our requirements. So the model is very good for building up and producing what we want in this particular case. We also want to use the model to design a custom lens so we can actually get the final beam size that we really need for LISA. So I will skip pretty much over the pointing stability one. This is old results. We've reported these before, just to say that the pointing stability is a factor of 3 better than required for an optical coupler of this type. That's measurements we did some while ago. This one, it amuses me slightly, to be honest, that the waist position and size surprisingly sensitive. And in particular here, we're building the thing up, we're doing all the measurements with the thing in air, because I work best in air, but it will in the end be used in vacuum. And air and vacuum have very slightly different refractive indices. And you put it into the model and you discover that refractive index is very slightly different. And you would predict that that would shift the waist position by about 100 millimeters. And as part of our model validation, we set out to try and test this. So we took one of our engineering models of the optical coupler, we put it into a vacuum system and essentially measured the waist position with air in the vacuum system, then evacuated it and expected to see a shift of about 108 millimeters. We saw 110 millimeters, which is astonishingly similar. Admittedly, the errors are quite large, but it's still showing, the modeling is predicting the right sorts of things, which is very nice. We also worried about the temperature of it, and we changed the temperature by about 20 degrees or so, 25 degrees actually, and that produced almost nothing, as you would have predicted. Another step of model verification that we tried was to take two different optical couplers and essentially point them at each other. And if we put the second optical coupler onto a hexapod, so we can align it in angle and displacement, then we can optimize the coupling. But what we can then do is, once we've optimized it, we can actually change the alignment by either displacing it in angularly or laterally, and see if the change in coupling corresponds with what we would expect to happen from our model for these particular optical couplers. We've actually done this with essentially 3 different pairs. We've got optical couplers that are significantly different in terms of waist size, because they're using different components, so that's what we would expect to have. But we can use that as an extra way to exercise the model by doing coupling between like couplers and between unlike ones. And in particular, a really nice result on the right here, the blue data is the prediction from the model. And you can see we're getting a coupling efficiency from one to the other of just over 90%, which is extremely good. But also the thing that I really like about this is that the red line you can see in this graph, or can barely see, is the lab data. And even for very large misalignments where the coupling has gone down from 90% to about 30%, the model and the lab data are agreeing extremely well. Put this in just to give you an idea of what I'm not telling you. There's lots of details in this that I don't really have time to go into, which I only got a couple of minutes left, I think. So there's detailed measurements of the pieces and exactly how we do that. There's a lot of detail in the modeling about the fact that the beam is not Gaussian. Some of the parameters are quite strongly coupled to each other and so on. Another detail is it's surprisingly hard to measure beam diameters. Different cameras will give you different results, particularly using different technologies. Different algorithms, even in the same data, will give you different results. And we spent quite a lot of time working through that. Not going to say anything much about backscatter and radiation testing, except to say that these have been done. They've worked out very well. And I would strongly encourage you to go and look at Max's talk, where he goes into much more detail in exactly how he's done these and how well everything has worked. So I will finish here with just summarizing the whole thing. So I would say that building and modeling optical couplers to LISA specification is a very well controlled and very well modeled process. And having this modeling that's working really well is absolutely critical, because we need that model to specify a custom lens that we'll actually use for the LISA files. And that's something that we have now specified and is now under manufacture. I suppose as part of that, reality and modeling agree. That was absolutely key to the whole thing, that you actually get the modeling that works very well. As I say, it's been used to specify the components for actually a final LISA specification optical coupler. And with that, I will finish and ask for any questions.
Thank you, David, very much. I'm really impressed by the progress made on the implementation of the optical bench, hearing from you and also from the talk of Yuan today. We have a question. We have two, actually. Alexander Schultz, is there a reason to prefer refractive over reflective fiber couplers?
Yes, I think it might seem a slightly odd reason. I think one of the reasons that I alluded to earlier is that we don't want any, at some point you have to get light coming out of the fiber. And you want, it's quite dangerous, I think, to have very high power densities. You're very much susceptible to laser-induced damage or contamination in various ways. So by having all of the expansion of the beam up to the millimeter scale or 2 millimeter scale happening inside fused silica is much, much safer in that sense. And it's essentially, once you've got to a lens surface at with a beam of the 2 millimeter scale, it's a much easier surface to manage, to clean, or whatever.
Thanks, David. Then there is another one. We have a time just for a quick answer. Paul Fulda. Well, then you have others, but maybe you can take them offline. Paul Fulda is asking, is there anywhere one can find your results on the differences between beam diameter measurement methods?
No, I think is the short answer to that. It's something we spent quite a lot of time doing.
Contact directly David to have.
Absolutely, yes. No, I'm more than happy to talk about it, but it's not something that's written up directly, I'm afraid.
Okay, maybe just a quick answer also to Jennifer Lee. How is the optical coupler held on the bench? Will there be packaging around the assembly you show?
Okay, so I think both you and I mentioned in passing hydroxycatalysis bonding, and that's how the optics will be secured to the optical bench. And that's actually, if you look carefully at the design, you'll see that there are polished surfaces perpendicular to the beam direction that will be used to hydroxycatalysis bond the fiber coupler strictly onto a post that goes onto the bench, but we bonded onto the bench in that sense.
Okay, clear enough. So thank you, David, again. And we move to Henri INCHAUSPE. I hope I pronounce it correctly.
That's perfect.
Okay, and he would talk about measuring differential acceleration on board LISA spacecraft, application to DFACS optimization and acceleration noise estimate. Henri is now at the Heidelberg University.
Yes, thank you, Rita. Can you see my screen well?
Perfectly.
Okay, perfect. Thank you. So yes, today I'm going to present a work that I've been done in collaboration with Martin Newitz and Orion Sauté and Peter Vass from AEI and University of Florida. This has been subject of research that just was out today, so that's perfect timing. And so the topic is like developing ways to measure differential acceleration aboard the LISA spacecraft with two applications in mind. One, for optimizing the suspension part of the control system. And one is deriving a way to build estimator of the acceleration of the test mass on board. So just a very brief recap of what is the LISA detection principle. So the basic idea is to realize in space a basic sketch of interaction between matter, meaning like you have a ring of particles, and this ring of free particles that deform by a gravitational wave passing through. As particles, we have the spacecraft, of course, and not a very good reference of inertia. So we house on board reference of inertia, which are the test masses, which are very good level of stability. So that part have been tested with LISA Pathfinder, verifying that, so shrinking one interferometric arm of LISA into one bigger spacecraft, we were able to see that the differential acceleration between the two test masses was compatible with Gaussian astronomy. But of course, with LISA, because now the test mass to test mass is 2.5 million kilometers apart, and it's broken down into three pieces, so test mass to spacecraft, spacecraft to spacecraft, spacecraft to test mass. We have much room for optical misalignment and geometrical imperfections that leads to imperfection and coupling to stability of the spacecraft, which was not the case for LISA Pathfinder, in particular T2Lex. So here for LISA, spacecraft stability is a key properties, and understanding well the cloud dynamics of key importance. So in that particular context, this work have been focusing on optimizing a DFACS and defining properly first, as the first step, control coordinates, in particular to mitigate suspension, to isolate suspension from spacecraft jitter. That would be the point today. So here, you see a sketch of the spacecraft, so a slice of the spacecraft on the X or Y plane, meaning the plane which is parallel to the solar panel or within the constellation and triangle plane. And so you see three bodies. There is in the identical system, you have the two test masses that are housed in like square cubic electro housings that are attached to the telescopes. And so the point of the control laws is to make sure that the test mass are at the center of the housings. They're well aligned with the inner wall of the electro housings. The telescopes points towards a distant spacecraft. And that's pretty much it. So you have all these constraints. So to measure the test mass position, you have two types of sensor. You have optical sensor on the axis of the telescope. We provide a picometer for square-root precision, so that's the best sensor on board. You have also capacitive sensing, electrostatic sensing. We provide more like nanometer and nanoradian precisions, both for longitudinal and angular displacements. And you have DWS, so long-range differential waveform sensing, that basically measures the incidence angle between the incoming beam from distant spacecraft and the photodiodes on board. And these two angles provide you information about the attitude of the spacecraft. So that's the basic idea here. And from that information, well, first on this sketch, I want to stress that two very important reference frames are the one attached to the spacecraft, which is the spacecraft frame where the x-axis points towards the bisector of the two telescopes. Z is normal to the solar panel and the Y is completely infrared. And you have also frame attached to the housing. That's where the test mass coordinates are defined. So X points towards the telescope axis and Y and Z are completely infrared. You can see that on the figure. So this sensor information are used to control the test mass. So whenever you see differential motion between the two test masses, you have no choice but to apply force on the test mass to correct this differential displacement, and that is done with electrostatically acting on the test masses. That's called suspension control. And whenever you see a common mode motion of the two test masses, it basically means that the spacecraft is moving, is shaking, and that you can control in correcting the spacecraft motion with micropropulsion, and that is called drag-free. Okay, that was so yes. So basically, that's what is DFACS, drag-free and attitude control system. Three main points: mitigate spacecraft jitter, that's drag-free. Maintain the spacecraft telescopes well oriented towards the spacecraft, that's attitude control. And compensate test mass drift one with respect to the other, and make sure they stay in place in the spacecraft, and that's suspension control. So we wanted with this work to optimize the DFACS coordinates in order to make sure that this common mode control, drag-free and differential mode suspension control are well isolated, so that you don't trigger force on the test mass, which come from which are triggered by the spacecraft agitation. So that you don't want to do, and in doing so, you mitigate the amount of force which is applied to the test mass. So you're defining very well common mode and differential mode. And to do that, the point is to build estimator of what is the differential acceleration you measure on board between test mass and test mass 2, test mass 1 and test mass 2. So that's a way of optimizing suspension. Instead of like purely suspending test mass on the motion you see of test mass 1 along the three axes Y, X, Y, and Z, you take all your sensors on board and you build estimator of what is the differential drift between the two test mass, and that will serve as a locking information for the suspension. So you end up with some coordinates here. So you see, for example, the main coordinates of interest here are the suspension one. So if you look at the bottom left equation here, which is a coordinate for longitudinal suspension, you have also a big picture showing all the coordinates, which is a bit busy, but you can find main coordinates, in particular theta, eta, and phi, which are respectively always rotation around X, Y, and Z, just for your information. So here, basically, the red square here is a measurement of the differential displacement between test mass 1 and 2 projecting along Y. Y will be the axis for suspension control. And you make use basically of the other test mass in order to measure against the observed differential acceleration proceeding along y, and that will serve as a quantity that you want to suspend. But when you do that, you have also another component you're not taking into account, is the fact that when you have your spacecraft rotate, it also induces an observational differential displacement with two test mass from a lever arm, and you need also to correct that in order to build a correct estimator of the differential acceleration. So that's the green component you see on the bottom left, and that you make use of the long-range differential waveform sensing, giving the attitude of the spacecraft. So that's the main part. For the suspension control, this is the same idea, except that now you want to be isolated from spacecraft jitter, but you still want to keep on with the rotation of the constellation around the sun. And to do so, you basically will make the difference between information of the rotation of the spacecraft from long-range TWS with difference from that with the test mass DWS, so the local measurement of test mass rotation here. And if you do so, you're able to reject spacecraft jitter and still be sensitive to the rotation of the spacecraft. Okay, so here are the full drag-free control coordinates we came up with. And now I'm going to demonstrate that using these new coordinates, we're able to confirm that we isolate suspension, so application of force on test mass from spacecraft jitter. We still, yes, so the rotation of the constellation will still trigger force on test mass, both in rotation and in longitudinal, in order to keep on, to rotate the constellation around the sun that we want to keep. That's a common mode suspension we want to keep. And that we still have the same term of stability of the degree of freedom. So for that, we use simulation tools that have been developed from for the consortium. One is purely linear, done in MATLAB, which is called LisaDin. It's enough for all the application we want to do in that work. But just for cross-check, we also use a full simulation for Lisa Simscape, which is the full geometry of the spacecraft and full nonlinear equation of motion. And both simulators agree on the fact that this new scheme is running well. So this simulator basically simulates the closed-loop dynamics of the system. So this feedback loop you see here, and I've been mentioning. And the idea is like to solve force time evolution of the 50 degree of freedom, meaning attitudinal spacecraft and longitudinal motion of test mass and angular motion of test mass of the two test masses. Okay, so first experiment we did, we injected a sinusoidal force on the spacecraft and verify what would trigger in terms of suspension force on test mass. If the thing is well done, then we trigger no force. So here you see the comparison between blue, red, and yellow. Blue was a simple scheme where you basically suspend all the degree of freedom, so that's a naive one. And the yellow one is like with this new scheme. And you see that the two lines we injected at 10 and 20 milliamperes completely disappeared. And the red one is with and without, so comparison between the red and yellow is with and without the level of correction. So you see that well, here we didn't inject a torque, but you still have a noisy torque coming from the source noise. And you see that it, in the case you don't correct for the lever arm, you still trigger some special suspension which are coming from the jitter. And so if you include this lever arm, it is optimal. So you can do the same experiment for the attitude, and it works perfectly well. So that's an analysis we've done in the paper. Now you want to verify that you're rotating well your test mass with the constellation around the sun. So what you do to simulate that is you inject a guidance at low frequency, a guidance of the force rotating the spacecraft at low frequency, and we can show here that so indeed this guidance triggers some suspension forces and suspension torque on the test mass that go along with this guidance. So effectively, you're going to have suspension force and torques that will accompany the rotation of the constellation. So that we keep. And then with the same experiment, we can check for these two same degree of freedom. So here, this is Y motion, test mass along Y, and rotation around phi. that for the simple and optimal scheme, we keep the same level of stability. You see this peak here. This is just the guidance we inject in that experiment. This is not of interest here. So the stability is the same. So if you look at the impact on noise BJ, the main impact is that if you have some actuation crosstalk, now because so all the actuation crosstalk contribution that come from noisy spacecraft motion, which suspension see and apply some unnecessary force, all that is completely cancelled with a new scheme. So there was not a limiting contribution to the budget, but now, because it's completely killed, we gain in robustness in more general. That was the idea. Now we can use the same philosophy to build estimator of differential acceleration, which is the test mass, but now projecting along X. And for what purpose? Now it's building an estimator for the acceleration noise now. And so this is the same type of equation you see here. So you use both the test masses to measure one respect to the other, the acceleration, and you correct for the lever arm. That's the same idea. And here we also correct for the commanded force here, because we want an out of loop quantity. So so this is not the acceleration you're measuring. This is a little bit. This is an upper bound to it. Because you also pick the acceleration noise of the second test mass partially along y-axis, along the y-axis. But still here it's giving you a good idea or an upper bound of what would be the acceleration noise, and can be very, very interesting for sanity check and also commissioning calibration. And so you can have a certain measure of the force you apply during calibration on your test mass. And that's super interesting. So to verify that this equation here were able to reproduce the force which are applied to the test mass, the noisy force are applied to the test mass, we did an experiment again. So we applied a sinusoidal force. I cannot see the amount because there is anyway. We applied the sinusoidal force on the test mass, and we checked if our estimator was able to recover this, and that's what you see here. So we were able to observe this. Of course, there is more noise, as I said, because you're also picking test mass, some of the second test mass noise. But still, this is a very, very interesting estimator. You can build a spectrum of it, and you can see indeed that you're able to pick to correct for the injection you see. And as I said again, compared to the true acceleration noise of one of the test mass here, you're like a certain factor above in terms of noise, because you're picking more noise in this emitter than the true acceleration noise you want to recover. Here in the paper, you have a whole analysis of decomposing all the contribution to the estimator and verifying that everything is. Okay, I think I'm pretty much done here. I will conclude this just with the fact that, so this building this estimator of observing directional acceleration was able to define better, more suited DFACS coordinate in order to make a better, clear distinction between what is common mode and what is differential mode. And in doing so, we were able to suppress completely actuation crosstalk driven by spacecraft motion. And doing so, it was enhancing robustness of laser performance. Advantages of this scheme is it's purely software processing. I mean, it comes almost at no cost. And if anything, I mean, in any case, you can change the scheme in flight for whatever reason, if you have failure of sensor or whatever, that's always something you can do. Possible disadvantage is the fact that now, because you look for each of the coordinates now involves all the sensors, it make me maybe harder to interpret your closed-loop system at the end. But in any case, you have all the coordinate mapping matrix, which is fully analytical, so you always can refer to that in order to better understand your closed-loop system. About the estimator of the differential acceleration, like it puts a very interesting upper limit on your performance of the test mass acceleration for both axes here, and it's also a very interesting estimator for calibration and data processing. Like if you want to measure a force you're injecting on one axis, or if you want to detect glitch, for instance, it could be very interesting to have this new observable. If you want to know more about this work, you can check out our new paper just out today. I will see the notification this afternoon. So you can just follow this link to have more details. Well, thank you very much.
Thank you, Henri. Thank you very much. Very interesting questions. Alexander Schultz, have you performed a model with shape noise as well? You stated only white noise. I would expect many noise sources contribute 1/f, which would be important to consider.
Yeah, so most of the noise I will is there some in the paper we specify the shape of all the noise, and as much as possible we took LISA Pathfinder like noise shape and values measured with LISA Pathfinder.
Okay, so you are measuring just you are measuring estimated differential acceleration between the two test masses along a certain degrees of freedom, right? Direction.
Yeah.
So, but because I was confused by you saying, because you were measuring acceleration noise locally. So it's a differential acceleration that you are measuring.
It's differential, but it's still locally. It's differential between the two test mass in the local spacecraft.
Okay, in that sense. Okay.
Yes, so that's why you have to pick a little bit of y acceleration of the second test mass, and that's your estimator is not perfect. That's what you see here, but still that's some info you may want to use because everything is purely local, and you have an idea of what is your acceleration noise.
Okay, so Alexander was also asking, are the models made available in the scope of the publication?
The model, the dynamical model, or the noise model?
I don't know, Alexander, would you? Alexander Schulze, would you? Simscape.
As a Simscape, no, I think it's still private. It's I mean, it's consortium. It's public for the consortium member. That was developed by Martin Whitson, so it might be better suited for than me to answer this question. This is specific.
Okay.
The linear one is accessible from people that are LISA membership.
Thank you for the answer, Alexander.
Thank you.
Okay. Thank you, Henri. Very interesting. And now we have the last talk of this session, given by Nils Frederik HASSELMANN of Airbus. And the title of the talk is Active Beam Pointing Control for LISA via Interferometric Angle Measurements. We can see your first slide, but it's not in the presentation. Right. Please. We can't hear you. Yeah. Frederik?
Okay, can you hear me now?
Yeah, perfectly.
Okay, perfect. Thank you again for the kind introduction, and welcome to my talk about active beam pointing for LISA using differential wavefront sensing as feedback. And here in this picture, you can basically, in the photograph, you can see the setup that was used to obtain the data. I will show you later. And a little fun fact, maybe, so the interferometer you see in the front on the right, yeah, some components should look familiar from an earlier talk given by Ewan. Here's the fiber launchers from Glasgow, and this interferometer was actually bonded by Ewan. Yeah. So okay, so let's have a look at what I will talk about today. So first, I will give you a brief introduction to the topic. So why is active pointing required, and what solutions do exist to tackle the problem? And what are the challenges that are coming up? Yeah? And then I will present to you the experimental setup in a little bit more detail. So I will talk about the layout of the setup and the function of the components. Then I will talk a bit about tilt to length coupling for small field angles. And this is highly interesting because it helps us demonstrating the feasibility of the alignment of a LISA representative telescope using TTL coupling effects. Yeah. And this is then followed by the alignment of the mechanism showing or simulating reenacting the motion of the distant spacecraft. And I will talk a bit about the challenges and techniques that were that occurred or that were used in the alignment integration and testing of the spacecraft simulator mechanism. And then I will show you the first data on active beam pointing that were obtained using the now completed system. And so this data is incredibly interesting and exciting because it helps raising the credibility of the mechanism technologies that are used for active beam pointing. And in my outlook, I will tell you what is next. So let's jump right into it. And so, as you may remember from Linda Mondin's talk yesterday, I think, so the inter-spacecraft angles or the apex angles of the LISA formation vary slowly over the mission duration due to orbital perturbations. And this requires that the telescopes must be continuously aligned to point at the distant spacecraft in order to maintain the noise levels required for LISA. And the solutions that were conceived to tackle this problem were telescope pointing, siderostat pointing, are also in-field pointing. And telescope pointing is a baseline architecture for LISA, where the whole telescope modules are basically pointed or moved. And in siderostat pointing, the first mirror that is encountered by the incoming light from the distant spacecraft is a folding mirror, and this mirror must be rotated and also operated in an additional linear axis, so it must be stepped. There's a stair and step motion going on of a linear axis in order to keep the TTL coupling low. In an in-field pointing, a very small mirror is positioned in an intermediate pupil plane of an off-axis telescope and does the beam pointing, reducing effects, for example, of self-gravity, because we only are moving a small mass. And all of these architectures have their benefits and drawbacks, but I don't want to talk about those today. I want to focus on what these architectures have in common. And all of these payloads require active closed-loop beam pointing using interferometric angle measurements, and they all suffer from TTL coupling. However, the in-field pointing concept enables end-to-end investigation of tilt-length coupling effects in a laboratory environment on ground, and also allows us to have a look at the alignment procedures for a typical telescope and measuring the pupils. And however, this is a cool thing, the results can be transferred to all the architectures. And with that in mind, let's have a look at the in-field pointing setup. So the experimental setup is shown in the top here as a sketch. Can you also see my mouse, by the way?
Okay, now now it's okay. We are looking at the fourth slide.
And can you see my mouse, my pointer?
We can see the mouse, yes.
Okay, perfect. So I will use this as a laser pointer. So here you can see the sketch of very much simplified of the setup. And on the bottom left, you can see a CAD model of the entire setup. And on the right, there's a picture of the fully integrated setup. And the setup consists of the spacecraft simulator reenacting the motion of the distant spacecraft, to be seen on the right here, and an off-axis telescope that is reflective and has a magnification of 5. And in the intermediate pupil plane here, there's the so-called in-field pointing mechanism placed that does the pointing. And then we have a refractive 5 times magnification stage and another pupil plane in front of the interferometer. And the interferometer here is shown very much simplified. So we have also auxiliary interferometers that are not shown here for a reference interferometer and a phase interferometer. And yeah, and so the interferometer has some optics here that are polarizing for beam steering, and another relay stage to complete the pupil imaging onto the quadrant photodetectors. So in total, we have 4 pupil planes. The first pupil plane being the one on the QPD level here, then one between interferometer and beam expander, and the third one being where the infield pointing mechanism is placed. And last but not least, the pupil where the spacecraft simulator sits in. Yeah. And so here, for example, the beam expander cannot be seen in the photo here because it's hiding behind the reflective stage, but you can see it here on the left. Yeah, on the left-hand side on the CAD, you can see it's sitting behind the reflective telescope. And I want to mention that all these, so we have mostly an all zero dual transfer function, and when there's metal, it's always like formally compensated. Yes. And now we are using the interferometer readout to derive, for example, our differential wavefront sensing signal, and that we can use for controlling the mechanical angle of the infield pointing mechanism, thereby performing the pointing. We can also, for example, apply a command to the spacecraft simulator in order to simulate an example, so an orbit of the distant spacecraft, so to reenact the motion of the distant spacecraft. Yes. So one measurement that's highly interesting now is the tail-to-length coupling for small field angles, as it allows us to demonstrate or to perform a measurement of the total system pupil offset, as well as to determine the pupil calibration accuracy. And also it allows us to show an effective telescope and optical bench alignment integration and testing, especially with respect to pupil alignment. And yes, and this is something that is really of interest for integration of LISA also later. And the measurement conditions here were that the spacecraft simulator is static, while the infield pointing mechanism is actuated, and this is happening typically at 5 microradians per second mechanical angle. And now we record the change in path length as well as the angle between the RX beam and the local oscillator beam by means of the quadrant photodiode signals, so differential wavefront sensing, and we perform a double pass through the setup. And so here you can see now the differential wavefront sensing angle in milliradians plotted versus the optical path length, and the slope of this data set gives us now the linear TTL, which is about, in this case, about 3.3 micrometers on interferometer level, on optical bench level. And if you transfer now to LISA, that we have a magnification of the telescope of 135, for example, you would obtain an external pupil offset of 0.45 millimeters, which is well within the LISA requirement. And the error is well below 100 micrometers. So also the accuracy is well better or well below the requirement. Exactly. So and this shows that for the ORATM, for example, and palm actuator, as well as for the hinge design, the lessons that we learn can be transferred to those. and the designs are very similar. So they are always like these solid state hinges are always used, Haberland hinges in combination with some bimorph piezo drive. To measure now TTL over large field angles, because the field of view of the interferometer is of course limited to 0.5 millirads appropriately plus minus, what is required is to reflect the beam back in itself, and this can be done by tilting the spacecraft simulator accordingly. But in order to do that, to tilt the mirror sitting in the external pupil, we first need a mechanism that does that. And this mechanism has also to be placed in the setup and aligned. And the optical tools we used for alignment were a laser tracker for the X, Y, and Z position, and the interferometer using differential wavefront sensing again to control the tilt in Nick and yaw. So Nick would be, if you look at, for example, the hinges here, these hinges, when so around this axis, if you connect the hinges, if you tilt the mirror around this axis, this would be Nick. Yaw would be perpendicular to that in this plane. And if you rotate the mirror around the surface normal of the mirror, perpendicular to both axes I mentioned before, then this would only contribute to the wavefront error slightly, and yeah, over higher terms. So this doesn't really have to be aligned that well. And for alignment, we used as mechanical ground support equipment, we used micrometer screws, and we also used a small rubber hammer to knock against the zero-dur component, so that it basically slides into place using slick stip, yeah, and that can also be used to align the setup. So you knock it around until it's there with micrometer precision where you want it to be. And so the characterization of the parasitic hinge deformation that always occurs using these hinges can be done before placing the mechanism in the setup. However, if you look at TTL measurements later, you can use certain measurement protocols that ensure that the parasitic motion of the spacecraft simulator mechanism doesn't contribute to the system TTL. And you can furthermore extract also the parasitic effects caused by the in-field pointing mechanism, so the mechanism used for beam pointing. If you have questions about this, I'm happy to answer them later. And so let's have a look at the first data recorded for active beam pointing, or the demonstration of active beam pointing. And here the goal was to demonstrate zero DWS control or DWS control, thus demonstrate basically an end-to-end laser previewing angle compensation. And the measurement conditions now are that the spacecraft simulator is actuated in open loop, and so with typically with a speed of some micrometers and nanometers per second, nanorad per second. And the in-field pointing mechanism is operated in closed loop operation to keep the differential wavefront sensing error angle at zero. And an optical encoder measures also the mechanical angle of the hinge of both mechanisms at all times. So there are two optical encoders, one for each mechanism. And so on the left here, now you see that basically, if you look at the gray curve that depicts the case where the telescope is static, so meaning both mechanisms are resting, and the red curve where basically the spacecraft simulator moves at a constant speed, while the in-field pointing mechanism compensates. you see that there's not really a difference, a vast difference between the two data sets, because this is an angle that is perpendicular to the basically controlled one. And if you look at the horizontal angle on the right, you can see that now the in-loop angular noise follows a shape that would be expected by using a PI controller in the frequency domain. So 1 divided by F noise becomes white noise, for example. Yes, and when for low frequencies we are limited by electronic noise. So we are sitting here on the reference and phase interferometer, on the auxiliary interferometers on the noise sphere. This can be seen from the comparison in the frequency domain, and the performance is now expected to be mostly limited by the control scheme as well as electronic noise of the QPD. So the control scheme is here a PI controller, but one could think, of course, of a more advanced control scheme. That's probably not really required if you look at the data, because it's well below the requirement, actually. Yes.
Frederik, I'm sorry to interrupt.
Okay, but we're already at the outlook.
Because we ran out of time, so please, if you can go quickly to the...
I can do it very quickly because we already arrived at the outlook. Yeah. Okay. So what is up next? So next we will measure the system TTL over the entire field of view by tilting both mechanisms macroscopically. So this requires, of course, much faster actuation for reasonable measurement times, but those measurements are expected to be performed by August or September this year. And to further validate active beam pointing, out-of-loop measurements are planned, which couldn't be done so far because, as you see, the last relay stage is only mounted in front of one QPD. The other one, the QPD on the right, there's no relay. The pupil imaging is not completed because we still wanted to do measurements of the longitudinal pupil positions. And but this will also be done, and then we can do balance detection as well as these out-of-loop measurements. And last but not least, we will investigate the impact of nonlinear TTL. That also depends on the method on calculating the differential wavefront sensing signal, actually, and also the alignment strategies may depend on how you evaluate the DWS signal. Yes. Okay, and with that, I would like to thank you, and questions are welcome.
Thank you very much. We use also the time for questions. So David, I see that he raised his hand. Please, David, ask your question. I hope that the answer can be quick. Go ahead, David. You are muted, David.
Was that this, David? You were...
Yes, David Robinson, you raised your hand, but maybe it was not.
No, I didn't raise my hand. I was just applauding. I enjoyed the talk.
Okay,
thank you.
Okay. So we have a question in the chat. Philippe, can you elaborate why no acousto-optic modulator was considered for the beam pointing, as the Japanese are planning for the cavity scheme?
So, yeah, that's a good question. And so the acoustic optomodulator, let's think about it. So for pointing, actually, so when we look at the angular stability, it should be possible to arrive at an Anurat stability levels, yes. But for the path length stability, because you're dissipating quite a bit of energy, in the acousto-optic modulator, and which leads to thermal noise, and that in combination with the relatively poor coefficient of thermal expansion, and that combined with the change of refractive index over temperature, will result in several picometer probably of path length fluctuation, violating the LISA requirements already. So while the pointing stability in terms of nanorad probably can be achieved, the path length stability won't be achieved. Yes.
Okay. So given that we are late, I think I have to thank you again for reporting on this, on the progress that you are making on this alternative implementation for LISA. And I thank all the speakers. I'm sure that you will get some questions offline. I thank all the speakers. I think I close this session here. And the Henri maybe wants to.
No, I think that's fine, Rita. Just to thank everybody for their contributions, and we look forward to seeing you all tomorrow at the beginning of the next session, which, remember, is a morning start tomorrow for those in Europe.
11 o'clock, right?
Correct.
Thank you.
So, good night all.
Yeah, good night.